on this computer. Of course, I'm going to narrate every little step I take in life. It's pretty much what I do anyway. All right, so first example there. Sketch the graph of the plane curve described by the parametric equations. All right, so we got x equals t squared minus 4 and y equals 2t. All right, so these starred problems, again, if you weren't here, they're just my indications that these are problems that I want you to look at before the next class. Right? It does, just because I start doesn't make it any more important than any other question. Right? So you see that we have some t values established for us, but we don't have x's and y's, so we need a table of values. You could use a graphing calculator if you want, a graphing utility online. It doesn't make a difference to me. But there's some parts of it where it's like, well, do we really need a calculator for that? Hopefully not, but you never know. So, and sometimes you just don't want to do the thinking, and I understand that too. So I'll start with the y's because I'm just doubling whatever t is to get the y value. So -4, -2, 0, 2, 4, and 6. Now I can go tackle the t values. Now, this is a parabolic function, the x equals t squared minus 4. If that were y equals x squared minus 4, then you'd have a better sense of what's going on. So, you know, like I have kind of a practiced hand when it comes to this because I've been, you know, teaching all of this stuff for so long that I can look at a quadratic equation and I just know all the characteristics of it just by looking at it. You know, we got a slope of 1, you know, that 1 unit slope of 1. We're going to be looking at something that's symmetric about the y-axis, you know, and all those things. But we also can just plug and chug like we did for the y equals 2t. So it's really up to you. But you could also, if you look at that 0, finding a y-intercept is probably one of the easier things that you could do. So I could plug in a 0, I get the -4. And then I can build outward from there. So, you know, the 149 relationship, if you like that. If not, then you just plug in a 1. What do you get? -3. That's what you would get if you plugged in a -1. Plug in a 2. 2 squared is 4, minus 4 is 0. Same for -2. Plug in a 3, 9 minus 4 is 5. So what we have here are sets of ordered pairs. We got 0, -4. That's an x and y coordinate. It's no different than it would be in an algebra class. So when I see the 0, -4, I would think of it this way: 0, -4. Right? So the 3, -2, same deal. Right? I don't have to put parentheses on all of them just so you can see that. I think we get the idea. So I plot the 0, -4. My scale is 1 unit, so that's fine. Frog in my throat. -3, -2. -4, 0. -3, +2. 0, 4. And then we're looking at 5, 6. Oh, okay. So now what we want to do is we want to plot these points. Well, we already plotted them, but we want to plot the curve in the order in which we plotted the points, which corresponds with the order in which the t values were given to us. Now, they were given to us in increasing order, so that is the order of the plot. So we start off with the 0, -4 and work our way around to the upper point, and then last time we talked about this, we just throw arrows on it to indicate the direction of the flow. This is actually the very first kind of entry point into the concepts. Oh, that got ugly. Sorry, gotta kind of fix that. into concepts associated with vectors and vector fields. So, there's some newness to this, but there's also some familiarity to it. Because if you remember slope fields from, it should have been Calc 1, you remember slope fields, then this is kind of along those lines, except we're just focusing on the curve and the flow of that single curve. We're not focusing on the flow of all possible slopes for every value of t, so it's different, but it's the same, right? It's like I said, it's an entry point into that concept, all right? And again, I put the little notation there, make sure you include arrows, because if you don't include the arrows, then I don't know which way it's going, because the parameter t indicates the position at a given moment in time, right? So it's not just a matter of knowing where the object is. I want to know where it is at a certain time, right? So that's critically important. Yeah, I kind of look at it like, in just off the top of my head, slash, this is the example I use every semester. If you have an intersection of two roads, doesn't mean there's going to be a collision at that intersection. There would only be a collision at that intersection if two cars were at the same point at the same time, right? So that's the difference in the gravity of the two ideas, right? Gravity is in importance, not in terms of the physical concept, right? So we have that whole blurb basically addressing what I just said, so I can just kind of gloss over that. Oh, trying to write with my finger and not a pencil. All right, the second one, you can see a little bit more complicated, but you have parametric equations again, projectile. The y equation looks very much like some variation of a position function. That -16 kind of jumps out at you. If you're looking at the 1/2 gt squared plus VOT plus SO, you get the 1/2 g giving you the -16. So it's feeling like that. But then you have that 20t. So you have a horizontal component of the projectile and you have the vertical component. The vertical component is really only impacted by the acceleration due to gravity because there is no velocity in the vertical direction. But the horizontal component has a velocity component based on, and it's kind of weird to say that because it seems like I'm using component too frequently, but it's really correct because the horizontal component, which is the component of the parametric equation, also has a component related to the velocity vector. All right, so more on that later, but we got to start somewhere. So just like the last one, in this case, not always going to bear out this way, but in this case, part of it is easier to handle than the other part. Multiplying by 20 is not complicated. So that's the x equation. So 0, 10, 20, 30, 40, 50, 60. And of course, once you get a sense of the trend in a linear function, you're not doing computation anymore. You're just carrying out the process. Plugging in a 0 for the y equation is just going to give me a 64. Plugging in a 1/2 now. I mean, you can get the calculator involved, like I said, or get a cal. I'm gonna trip over that a lot by saying the calculator because it's always been the specific calculator, but really it's any calculator as long as it doesn't do calculus for you. I have no preference. So anyway, yeah, 1/2 squared is a quarter. A quarter times 16 is 4, so 64 minus 4 is 60. I don't know why this thing's glitching on me. Straight up, 64 minus 16, so 54, so 48. It gets a little kookier after that. So maybe you want to get the calculator involved. Maybe now it's just a point of pride. I don't know. We'll let you decide. But for you anyway, for me, it's always a point of pride. So The 1.5 is 3/2. Square that, you're getting 9/4. 9/4 times 16. We're talking, the 4 goes into 64 times, so 12, if I'm not mistaken. No, there's a 9. No, hold on. So it's 64 minus 36, right? Because it got a lot smaller, a lot quicker. All right, so that would be, so 20 gets me to 4, so 28. I don't want to know that I'm wrong. I can't just let this moment go.
Yes.
Correct.
It's right?
Yes, it's 28.
It's 28?
Correct.
Oh, wow, look at me. I think I'm a math teacher or something. Anyway, yeah, broken watch is right twice a day. So for 60, so next one's 0, right? Then after that, I guess we kind of don't care about it anymore, right? Because now that's true and it's not true. We'll get the other points in a second. We don't know the context here. We don't know what kind of projectile it is. But if we assume that it's an ordinary projectile, like a ball thrown in the air, that is something that's not going to dig into the ground, then we're probably going to assume that once it hits the ground, we've lost interest in it. But you know, it's not necessarily going to play out that way. So, since we don't have the context, we just got to assume that maybe there is some value to some negative y's. So 5/2 squares 25/4. So that is, so 25 or 16 divided by 4 is 4 times 5. Oh, times 25 is going to be the 100. So negative 36.
Yes. Professor?
Yo.
Can you hear me?
Yes.
Okay, just making sure.
Then we have 9 times 16. Is that one? That's 144. So this is negative 80, I think. (64 minus 144) feels right. All right. Well, it's not a course on mental math. It's a course on calculus. But, man, get this far, you got to kind of sort of get to a point where maybe you don't love the math, but you got to at least kind of appreciate it. So, and, you know, for me, I like to challenge myself, but I also like, I just like the content. So here we are. Anyway, and by the way, if any of these are incorrect, just chime in and let me know, or send me a message. See, the issue that I'm going to constantly be running into here is I don't think anything related to the chat is actually, I'm going to pause the recording for a second. All right, so just help me not be worried about that. Now, in terms of scaling, we got an ordinary x and y axis. Now, the x axis, they could make sense to go by tens. Now, I wouldn't think that you would need to label all of these the way I did. I mean, if you just want to say x by tens over here, you know, x, and then just make a note that you went by tens, I'm fine with that. Most people are too. In terms of the y's, we want to get as high as 64, but then get as low as 80. So 1, 2, 3, 4, 5, 6. Well, I'll go for the 5, I guess. Well, actually, that would have it go. Oh, we can go by 16s. I mean, it's not ideal, but we can deal with it. I mean, you could go by 25s and estimate. You can go like whatever you want. I'm just trying to get some clean points here. And it's not always going to work out, but but we'll give it a shot. So 0, 64, and you can go red there for those who scored home. 10 and 60, ballpark estimate, right about there. 20, 48, I believe that's a gain. 30, 28. So like around here. 40, 0. 50, negative 36, ballpark estimate, meh. And then the final one, 60, negative 80. All right, and we know that we start at the highest part and work our way down through the ground, burrowing 80, I would imagine, feet based off of the nature of the model.
I have a quick question. It might be, does T always go in the direction like negative to positive or like 0 to 3?
Unless you're told otherwise, yes. Right, because we're going to learn how to change coordinate systems down the line, and it's kind of weird to think about it, but we're going to look at some cases where time will be interested in time flowing in the negative direction, but we're going to reestablish that as a positive flow of time. You know, so I mean, I haven't seen the movie Tenet yet, but my understanding is that's kind of along the lines. So that's a reference that anybody understands. But yeah, like going backwards in time, but your perspective going backwards in time is forward. Right. So that's the only twist that would take the flow and reverse it. Right. So basically, the short answer is very, very rare, but it could happen. Let me pause. All right, so now we're flipping on down the line. So we got that squared away. You know, diagrams look pretty awful when I zoom in, but like a shrinky dink, when I zoom out, it doesn't look too bad. But like I said, you know, if you get the GoodNotes app, then you can fix all my diagrams as much as you want. So oh man, my handwriting is bothering me. I gotta be a little bit more careful. So page 4, we talked about the idea of converting from parametric form to rectangular form and vice versa. And rectangular form, all that means again is x, y. Right? So we want an equation in terms of x and y's, but we have equations that are in terms of x's and thetas, or x's and t's, y's and thetas, y's and t's. We want to get rid of the t. We want to get rid of the theta in these cases, in some of these cases. Or we can go the other way, where we have an equation that's strictly, like looking at example 10, an equation that's strictly in terms of x and y, and we want to introduce a time component. So yeah, you start thinking about it like, okay, you got a parabola, but what if an object is moving along that parabola at 50 miles an hour? You know, like what would that parametric model be like? You know, that's what we'll be looking at. But for now, we're just focusing on converting back and forth. So last class, we talked about a couple of different ways to get from one form to the other, especially involving trig. And it really boiled down to the one key concept: just grab a rule that you know to be true and use that to help you to eliminate a parameter or introduce a parameter. Right? So I'm going to highlight this one, because if you go right on back to college algebra or algebra 2, or you know, wherever you were, you probably saw this one a lot. And this is the Pythagorean identity for the unit circle. It's actually the model for the unit circle. Sine squared plus cosine squared equals 1. Right? It's a known identity. It's always true. No matter what value you put in for theta, it'll always give you a true result. Right? So we can rely on that information. So when I'm looking at something like number 6, and you see the parametrics that are given, x equals 3 cosine theta and y equals 4 sine theta, you might look at that and say, I don't know what this is. I don't know what this is supposed to be. If I gave you a multiple choice question, I said, okay, is this a line? Is it a parabola? Is it a circle? Is it an abstract drawing of a turkey? You know, like what is it going to be? Maybe you know, maybe you don't. But if you convert it over into rectangular form, you might be able to recognize the standard form notation kind of creeping out from the messy algebra that you have, and from there be able to say, oh, that's what it is, right? So that's what the goal is for this. I don't know why I keep getting iCloud errors on my iPad, and it's annoying me. So I gotta figure that out at some point. So anyway, first thing I'm going to do is I'm going to isolate the cosine theta and the sine theta. Not too challenging. Because all we're doing is just dividing a couple of things. Trying to make the handwriting look a little nicer. It's never going to be nice, just nicer than what it was. Okay, so we know that, so the rule, old school rule, sine squared theta plus cosine squared theta is equal to 1. You were told way back when that it was important. You either believed that it was or you didn't. And as time went on, so you took algebra, pre-calc, calc 1, calc 2, you heard it repeatedly, and repeatedly it was confirmed to be a true statement. Very, very important rule. You can't make it through this course without knowing this rule. I mean, I'm giving it here in the notes, but it's a non-starter. You gotta know your unit circle facts, right? So, and that there is no exaggeration there. And it's not to scare people, because the unit circle is, spend an evening. If you struggled with the unit circle in the past, it's because you probably didn't spend too much time trying to memorize it. But if you take some time and sit down and look at it, I don't know why. I don't know why that just happened. So anyway, if you take some time and try to memorize it, you'll get it, right? And I have resources for that. Oh, and by the way, I'm gonna kind of force you to do it, right? Because I have a couple of activities, online games, and there'll be quiz grades associated with it, so it'll be fun. I try to make it fun anyway. So study the unit circle. I'll send out a link in a little bit, little ideas for how you can go about doing that if you're struggling with it, because that's how important it is, right? So we know that cosine of theta, well, I'll start with the sine of theta. Sine of theta is equal to y over 4. Cosine of theta is equal to x over 3. So I have a direct substitution here. Because I can pop this guy in right here, make it y over 4, replacing the sine with just a y over 4. And then I can pop this guy in. Let me see. I'm gonna go purple for those keeping score at home. We have x over 3. All right. Now you may look at this and say, I still don't know what this is the equation of. And your instinct might be to solve for y in terms of x. That's fine. You can do that. There is a slightly more advantageous way of handling this. Square both sides. Square appropriately. Square the fraction. So y squared over 16 plus x squared over 9 equals uno. And then just cleaning it up, and cleaning it up just means I'm just moving some things around. So x squared over 9 plus y squared over 16 is equal to 1. All right. So that, if you recognize it, that's great. If not, then you got to start thinking about what's the best way to come up with this graph. This is the equation of an ellipse. And you could start getting into the characteristics of the ellipse, but that gets you down a pre-calc rabbit hole that maybe you don't want to go down. I got to say, as a student, pre-calc was my least favorite course. As a teacher, it was one of my most favorite courses because I knew where the journey ended, because I didn't believe any of the stuff we were learning in pre-calc was really as important as what the teacher said it. You know, you're not going to succeed unless you know this stuff. Well, yeah, I probably will. And then it's like, oh, I really do need to know this. You know, ellipses kind of fall, anything in conic sections, ellipses, hyperbolas, parabolas, all that good stuff. They all kind of fall into that category of like, they could never possibly be as important as they're making it out. And they really, really are, right? So what's the moral of the story here? Unit circle, know your, or at least have access to, because we're in a remote environment, so have access to the standard form equations for conic sections, right? So, I mean, just Google that and you'll have it. And I'll send out resources for that too. But standard form equations for conics is kind of where you want to spend some time also. In terms of the graph, I will say that using technology, it's easier to graph. Old school calculator notwithstanding, it's generally easier to graph conics in parametric form than it is to graph them in function form, because you have to graph them as a piecewise, you know, as two separate models, and so that becomes problematic in and of itself, because then it's like the two functions have to connect, whereas in parametric form it's one seamless curve. We can talk about what these look like in a little bit, but for now, let's just move on to the next one. Now, you'll notice that in number 6, the leading coefficient for cosine and the leading coefficient for sine were different, right? And that leading coefficient of 3 corresponded to a denominator of 9, and the other coefficient of 4 corresponded to a denominator of 16. So there's something to that. Sorry, I tripped over my own wires. So what about the cases where the leading coefficients are the same? Well, we know again that we have this rule, sine squared plus cosine squared is equal to 1. All right. Now, fun fact, it's not just of theta. So the general rule, I don't even know why I try going in script. It never ends well. Is really that it's sine squared of really anything. You know, it could be the sine squared of a function as long as that function exists. So I'll say of u plus cosine squared u is equal to 1. You know, I play that off like I just came up with that on the fly, but that's what the rule is, you know. And so in this case, I would say sine squared of 2 theta plus cosine squared of 2 theta is equal to 1, where u is equal to 2 theta. And that's a true statement, right? So what we're looking at here is another direct substitution case, because this is something squared. This is something squared. The sine corresponds with the y. Cosine corresponds with the x, but if you clean it up, you get your standard form equation for the unit circle, x squared plus y squared equals 1. Okay, center at 0, 0, radius of 1. Now, the 2, the coefficient of 2 in front of the theta, all that does is it impacts the number of trips around the circle. It's the frequency. You know, like if you think about a sine wave, if I have a frequency of 2 as opposed to a frequency of 1, you know, it's like how many full sine waves am I going to get in the 2 pi period? Well, 1 trip around the unit circle is 2 pi radians. So when I say that the frequency is 2, I'm saying that I'm just taking 2 trips around the unit circle, right? Now, we're also we have to be respectful of the domain where it says 0 to 2 pi. So we have to take that into account. But at this point, I'm just looking for regardless of the number of trips around, regardless of the movement, the actual physical movement around the circle, I just want to know what the path would be. So it's the car on the road versus the road itself. So do I want to know where the car is on the road, or I just want to know where the road goes? Right? These are cases where I just want to know where the road goes. All right. Number 8, we have an inexplicable change in font here. So if anybody's looking for typo bonus, that's an opportunity. But yeah, same for the next one. I know why it happened. I just don't know why I didn't fix it. So number 8, you can see here that it's very similar to number 6, except we're working in general terms now. But that's fine, because the same skill is going to be at hand. Divide by A, divide by B. All right, boop, boop. Couple of boops, lots of boops. All right, so we have cosine of t equals x over a. Sine of t is equal to y over b. All right. Now, we also know that sine squared plus cosine squared is equal to 1. We also know the reverse is true because addition is commutative. Almost said multiplication is commutative. That's also true, but not relevant here. So I can just take, if I want to just kind of cut to the chase, I could say cosine squared u plus sine squared u is equal to 1, which would then, if I square this and square that, I get x squared over a squared plus y squared over b squared is equal to 1. And, you know, it's an exciting moment if you remember that this is the standard form equation for an ellipse. Specifically one centered at 0. Specifically 0, 0. Yeah, so that's a great aha moment. Again, if you have that knowledge, you know, that prior knowledge. It's tricky though, you know, like in my experience, you know, I got 15 students in this class. It's like a flip of the coin as to whether or not people have experience where it may have been skipped when they took the class. You know, this is all pre-calc stuff. Maybe they skipped pre-calc altogether. I don't know. But the folks who are familiar with these formulas are looking at this like, oh, that's pretty cool. So now what you gain from this is just on a sight recognition, you can determine that a parametric equation is going to yield an ellipse. Like you're looking at something that's going to give you an ellipse. So cosine, sine, x equals cosine, y equals sine, with 2 different coefficients, same coefficient circle, different coefficients ellipse. That's pretty cool. But then it kind of begs the question, what would happen if they were reversed? You know, would it still be an ellipse? You know, what if it's the x that's the sine and the y that's the cosine? Fun fact, it's still going to be an ellipse. It's just going to be a different orientation of the ellipse. One is going to be symmetrical, well, they're both going to be symmetrical about the axes, but one is going to be wider and the other is going to be taller. All right, but it's still they're both going to be ellipses. Now, number 9, this is a complete crapshoot. I don't know. It's an optional topic for Calc 2. Like I said, it is so hit or miss as to whether or not anybody has ever seen this concept before. Hyperbolic trig functions. It's not a requirement for this course, but I can't, in good conscience, conscience, I almost said conscience. I can't in good conscience talk about ellipse equations and circle equations, parabolas we already talked about a little bit, just not in their trig form, without talking about hyperbolas. Hyperbolic trig, hyperbola, you know, so, you know, it goes hand in hand. So there's a rule here that I'm going to share with you that you're going to look at, and it's either going to be, oh, I've seen that before, or you're going to be like, okay, you're just making stuff up now. And that's fine. I'll accept either. This particular type of question will never be on a test, right? But there's a good percentage of us that we just want to learn some math. And so that's what I'm doing here. Sometimes I do that. So anyway, we have cosine with the extra h, which it's hyperbolic cosine. But what a lot of people do is they just call that cosh. And instead of SINH as hyperbolic sine, we call that, it wasn't my idea, I didn't create this, cinch. Right? There's no C in there, but it's still like sin, like dude, your breath stinks. I don't know, like it's not gonna work out. So what we do is we just say cosh and cinch to make it kind of a little bit more reasonable to say repeatedly. So hyperbolic cosine of t is equal to x over a, and then hyperbolic sine is equal to y over b. All right, now here's the thing that's going to seem like I'm making it up. So the rule, and this is all specifically related to hyperbolic trig, is that cosh squared of u minus sinh squared of u is equal to 1. All right. So it's a negation relationship that has to do with hyperbolic trig, but it comes from the idea that in hyperbolic trig you don't have a unit circle, you have a unit hyperbola. All right. So instead of it being the sum of two squared trig functions, it's the difference between those two squared trig functions. Right? But that's really all there is to that, because the rest is just plugging and chugging away. So we have x over a squared, y over b squared, complete with the minus and the equals 1, clean it up, and you get your unit hyperbola equation. All right, so oh, it's actually not the unit hyperbola. Sorry, I misspoke. It's just the standard form hyperbola. It would be unit hyperbola if there were no denominators. If it was just x squared minus y squared equals 1.
Sorry, so where did I got lost? Where did H go?
H got swapped out because the cosh of t was equal to x over a. So based on that rule, I'm able to take the cosh of u, which is really t, and square that. And since that really is, let me get my highlighter here, that's really equal to x over a, instead of, well, trying to think, yeah, it's because the H is part of the notation. I just want to make sure I clarified that part of it. So the cosh is like, it's a new term. So it's not like the H itself went away. It's more like, and let me show the intermediate step.
So H turned into T?
The H itself didn't turn into T. Really what happened here is we have a rule that translated into cosh of T squared plus, minus sinh of T squared equals 1. So that's based off of this rule. So once I got to this, I just kind of did it behind the scenes. I swapped out the cosh of T for what I know it's equal to, which is the x over a. So that gave me this. So the x over a went in for this entire term, cosh of T, all in one term. The x over a got plugged in for that.
Oh, so just like how you would replace it in the other one, right?
Exactly. It's just
Right.
weird new notation, so it always seems a lot more complicated than it is. And then the y over b, same deal. It gets popped in for the sinh of T. The entire term itself gets pulled out, replaced with the y over b, and then the rest of the way.
Okay, I get it. Thank you.
No problem. Actually, now that I see that, let me. Okay, so we have that model, and like I said, it's for the sake of learning, the fun of learning. We want to learn some math, so that's where that came from. But it's not something you won't see it on the test or anything like that. But you know, like I can't speak for where you're going after this, so you know, it's definitely worth taking a minute to look it over together. Something is okay. Yeah, I just hit something with the mouse. All right. So then going the other way, we're converting a rectangular equation into parametric form, right? So that's a little bit of a different story. And usually when I say something is a little bit of a different story, that usually means it's much harder. It's actually the opposite of that. This is way easier, right? Because all you're doing is swapping out the variable x for some known relationship between x and t, all right? The good news is that relationship is either given to you or you need to decide upon it yourself, right? So you either are going to collect some data and come up with a relationship. Oh, it just turns out that t always moves at half the speed of whatever the value of x is. Or, you know, anything you think of along those lines. Or a question will flat out say t is equal to 5 times x. You know, so looking at the first one, we have t equals x. All we're doing is a direct substitution. So I have x, x. Oh, I can highlight the one more thing. X, and this x is equivalent to t. So y, instead of being equal to x squared plus 2x, is going to be t squared plus 2t. All right, now we clean it up. Not much cleaning to do in that case. And we have an equation where y is in terms of t. So the only thing we have to do at this point is represent our final answer, because it should be into a parametric equation form. So it should be an x function of t and a y function of t. So I would say x equals t, y equals t squared plus 2t. Now there's other ways to write this, and we'll learn about all those other ways as the course progresses, but for now we can just write it like this. So you have now parametric equations that incorporate a time component, but this time is really saying that whatever the x value is, time is moving at that rate. There's no context given, so I can't make a determination of whether or not that makes sense. You know, so if, you know, time, or I'm sorry, if the x distance, you know, like if a person's going up and down a roller coaster and the x distance is measured in feet, are you going to travel in lockstep time-wise for every foot horizontally that you travel? So, you know, for every horizontal foot, will that correspond to one elapsed second? Probably not. because once you go down that roller coaster, your speed's going to pick up dramatically, and so things are going to change. So we don't really know, but in the absence of context, this is the best we have. So in the second case, we have t is equal to x over 2. And again, all I want to do is swap out the x's for t's, right? So I got to do a little bit of extra work here, but nothing too complicated. So I'm going to cross multiply. And I'm going to get x times 1 is x. And we're going to get 2t. And then I'm just going to do that substitution, right? So y is equal to, again, t squared plus 2t with the 2 parentheses, but then 2t is getting plugged in for the x. So 2t, 2t. Clean it up. Y is equal to 4t squared plus 4t. All right, and so then we just have to state our final answer. X is equal to 2t. Y is equal to 4t squared plus 4t.
Can you slide it over a little bit? It's like cutting off some of the, yeah, there we go. Thank
No
you.
problem. Not a problem. So, yeah, it's not too bad. There's a little bit of legwork in that case. I mean, obviously, I don't think I need to say this, but if you have some really, really convoluted, complicated relationship between x and t, yeah, okay, so maybe there'd be a little bit more work, but it's really just substituting because you have the relationship between x and t. You're going to have to solve that for x at some point, so you might as well bang that out right away, and then make your substitution from there. So when you get to the last one here, it's like you kind of have a groove going. You say, okay, well, I got to solve for x in terms solve for x in terms of t. So we're looking at x equals t minus 1. And then we're popping this in just like we did before. Y equals squared plus 2 times smidge over there. Pop in the t minus 1, t minus 1. Now it's just a question of what's the value in simplifying this? Is there significant value? If the answer is no, then don't simplify. But if you have a reason to simplify, then simplify. Right? I'm not overly keen on, I'm not overly keen on doing work for the sake of doing work. But when it comes to simplifying quadratics, I'm a factor before distribute kind of guy. So I'd be looking to pull out the t minus 1, which actually means that I could have taken out the x in the original function to begin with, but that ship sailed. And so when I pull that out, I have t minus 1 plus 2. So t minus 1, t plus 1. So that's just going to be t squared minus 1. Now, you might have just distributed all, FOILed out the t minus 1 squared and distributed the 2. That's fine also. I didn't want to do it that way. I've gotten to the point where I try to at least consider the nature of the equation before I dive in with brute force tactics. Because, like 20 years ago, I would have been like, all right, distribute, and then blah, 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 without even really thinking about it. Now I want to take the moment, take the time, and do a little bit of thinking before I get myself into hot water. Yeah, that's an old teacher thing. I learned that the hard way. You fill up an entire classroom, with notes to solve one problem, and you find out you could have done it in 2 steps. And it's like, if only I took a moment and thought about it. Now, I'm not saying this is that, but it's something to consider. Just don't always go after it with brute force tactics. Sometimes just take a second and think about it before you dive in. All right. So that's page 4. So that's parametrics, you know, in terms of the conversions back and forth and stuff like that. Now, what we need to do is actually use this for something, right? So that's kind of where the journey is going to progress towards. So a lot of Unit 1 is learning about what seems to be disconnected concepts, and it'll seem like, oh, we're just going to jump from this to something completely different, and then what, you know? But they all come together later on. It's sort of like I was going to say a Star Wars movie, but like a good one, not the crappy ones, you know, like, well, even the crappy ones do the same thing. The heroes usually start off, I'll just go with ones where they started off to get like the I think we'll all agree Empire Strikes Back is the best one. Yeah, they all start off together, then they split up and they go on their separate ways, and nobody knows what anybody else is doing until the end, where they all kind of come together, you know? And so not to compare this course to Empire Strikes Back, but it's along those lines where we have a divergence of content, and then later on it all comes together, and you're like, oh, that's why we learned about all these different things. So, you know, with that being said, you know, another skill is a parametric form of derivative, and you're like, okay, well, I guess we learned about these parametrics, so why don't we just take a derivative too? And it's like, okay, that sounds like fun, but it's so completely different than what we just did that it feels like it's disjointed, right? I mean, I guess it's a progression of it, but it's not. Oh, that's weird. I think my other computer is listening to me because it heard a word that I said and it just put a definition of that word up on the screen. So I don't know what's going on here. Yeah, so we want the natural progression to feel just that. We want it to feel natural, but sometimes it just doesn't. Right? So if a smooth curve C is given by the equations for x equals f of t and y equals g of t, then the slope of C at x comma y is equal to blah, 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 right? So you look at this, and hopefully, you know, as we go through it, it'll make some semblance of sense. But we do have this new term here, and it's a new twist on a familiar term. So in Calc 1 and Calc 2, we would say if we have or given a continuous differentiable function on a closed interval a to b, or open interval, depending. Here we just say a smooth curve, right? Because we're not always concerned with continuity and differentiability, at least in the same way that we were in single variable functions, and also in rectangular coordinate systems. Because if you think about it, you could have a function in Calc 1, if it ever went vertical, all right, so like a sideways parabola, you would have a derivative that it wouldn't be differentiable at that point. You'd have something that had a vertical tangent, right? And so here we're okay with that because we're defining functions that are going to curve and repeat upon themselves repeatedly. We don't have the need for things like the vertical line test or anything along those lines. So the rules kind of change. What we want is a smooth curve. So what does a smooth curve mean? It would actually just goes back to the elementary definition of continuity from Calc 1. Before you started getting into all the limit stuff, it was, can you draw the curve from beginning to end without picking your pencil up off the paper? Okay? Later on, you found out there was more to it than that, but the smooth curve here, that's our working definition. All right, so dy dx, this is going to be a strange experience because we're looking at dy dx as the division of dy dt and dx dt. All right, so dy dt, the derivative of our y function in terms of t, dx dt, same thing but with x. Now what happens here is that because dy dx, dx dy, dx dt, dy dt, whatever. It's notation for differentiation, but it's also, and we can never lose sight of this, they're also ratios, right? And ratios can be operated upon, right? So this is the division of two ratios. So the dt's would then cancel away, right? And that's just going to leave us with dy dx, right? So we can get a dy dx. We can get the slope of the instantaneous rate of change of y with respect to x for, you know, in terms of that infinitesimal change in x, having nothing to do with the parameter t, right? Just simply by taking our dy dt's and dividing it by dx dt's, right? So let me just, because I think, I know I definitely have an example on the next page, but let me just throw an example your way right now. So let's say you have x equals, I'll say x of t just to make it obvious. And I'll go with a trig example here. Cosine of t and y of t is equal to sine of t. All right, so if I want dy dx, I'm going to first find dy dt. So I like to do a little crisscross action here. Dy dt, the derivative of this one. Now, you know, parametric, we can give it a fancy name all we want, but it's still a function of one variable. So the derivative of y with respect to t of sine of t would be cosine of t. And then dx dt, the derivative of my x function in which the independent variable is t, derivative of cosine is negative sine, still a function of a single variable, so negative sine of t. All right, so if I want dy dx, kind of smidging it over, so dy dx is going to be the ratio of these two. It's going to be cosine of t divided by negative sine of t, which you could simplify because that's one of the reciprocal trig functions, cotangent, negative. So negative cotangent of t. So we have a derivative dy dx. This is going to be a slope, right? Instantaneous rate of change that is relating y and x, but is dependent on the value of t. All right, so that's some pretty weird stuff because it's reliant on a variable that's not in its makeup. All right, so dy dt, the rate of change in height compared to change in, you know, horizontal movement, but strictly dependent on whatever the time is that has elapsed of that movement. Right? So, and you know, the units are still units. So would we use t units like seconds? No, because the derivative is the rate of change of two distances. Right? So, you know, it might be something like feet per foot, could be feet per inch. You know, it's something like that, but it's still going to be x and y relating to the units, not the value of time. So it's not, and this is where people kind of fall short on this, is they tend to think that okay, this is velocity, right? It's got t in it, so meters per second. Just throw meters per second on at the end. I mean, it could be meters per kilometer. Yeah, it's something along those lines. It's what's the units for y and what are the units for x, right? So it's something you got to keep in the back of your mind. And I've had many students over the years. What they do is they look at, okay, the units for y are feet, the units for x are feet. Feet divided by feet, well, that cancels out. So this measure has no units. It's a rate of change. It has units, right? So it would just be feet per foot, you know? So inches per inch. You know, it's very strange, but it's very important also. Right? The second derivative. Now we're getting into really, really strange territory. So the second derivative, now bearing in mind that this is all in terms of t. So it's not like I can just take the derivative of my derivative. You know, it's not going to play out that way. Right? So what we need to do, well, it will, just not in a way that you would think. So I have this all typed out here, but it doesn't always land. So let me just kind of take it from scratch here. If I want to find the derivative, so the derivative with respect to t of this derivative. I'm sorry, deep. You saw nothing. It's the second derivative. It's not. I was treating it like a related rates kind of thing. It's getting my courses confused. It's part of age and just being overwhelmed. So we know, and you know, we could kind of follow along here, but we know that d dx, based off of what we've seen, I didn't zoom out enough, and I've just realized that I can't just point to my screen and have you know what the hell I'm talking about. So let me just do that here. We know that dy dx translates to dy dt divided by dx dt. All right. Now, what I just wrote there in black doesn't quite feel like it's the same, but if I write it in ratio form, so if I write it as, okay, I'm taking the derivative of dy dx and dividing it by dx dt, it fits that model, because if you just kind of go back to that thing that I just highlighted, I'm going to do it really small here. We have this rule that says the derivative of, and I'm going to use air quotes, the derivative of y with respect to x. So dy dx. What y? That y. What's y? Y is y. But what if y was dy dx? Right? So I can actually take this notation, and this is the key ingredient here. So I'm gonna take this notation here. I'm gonna copy it. I'm gonna bring it down here eventually and paste it. I'm gonna make it a little smaller. I guess I'll chuck it over here. Hopefully it's still on the screen. I'm going to bring it in a little bit. And so instead of saying dy, I'm going to say d something else. That something else being dy dx. So everywhere that I originally had a y is now going to be replaced with that dy dx. All right. So previously, it just looked like it's all the same. You know, we got this formula. I'll just plug into the formula and we'll go from there. But this cleans up to what I wrote over here, because we're looking at dy dx with respect to x, and then dy divided by dx dt. All right, so it's a little bit on the strange side, but well, also it kind of helps if I don't screw up and write the wrong thing. I apologize. This should have been a t, because it's dy Here's my y. This whole guy here is what was y. And here's my dx dt. So dy dt, dx dt. All right. This is one of those things where I'm kind of beating it to death. I feel like I'm over explaining it. Hopefully I'm not making things worse by over explaining it, but the reason why I am is because historically, I'm just going by my own experience. The first 2 or 3 times I explain this concept, it's like, oh, what? We don't know. And then eventually, you know, based off of reading the reactions of the room, I can tell when people got it, but I can't, it's a different environment. So here we are. But yeah, chime in if you need another look at that one. Or if you just want to say hi, I guess. I don't know. I am going to pause the recording. So I just wanted to get through this this theorem, the arc length in parametric form, because of a couple of reasons. One, I don't want to overemphasize things, because I run into dangerous territory there where I keep saying that something is so very important, and then the next time I get to another topic, I say how important that one is, and then how important the next one is, and before you know it, it's like, okay, listen, you can't tell us that things are important because everything in this course is important according to you. So I'll try to kind of dial it down a little bit, but this one's kind of important, because later on in the course, when we learn, it's called parameterizing a function. When we learn about vector value functions, you know, converting, well, I don't want to get into that because that's a whole unit in and of itself, but we're going to learn how to parameterize, so create a parameter based off of the arc length of a function. So if you don't know how to find an arc length, then it's all over. So the first part of this equation, the s equals the integral on a to b of dx dt squared plus dy dt squared dt, should look fairly familiar, because that's not very different from, I mean, there's some tweaking going on, I'll give you that, but it's not very different. It's not absurdly different from the arc length formula from Calc 2. And one of these days, I'll show you how one became the other. It's kind of cool, but it's really just substitution, right? The alternate notation, you know, the f prime of t squared plus g prime of t squared dt, that's just for convenience, all right? So what I did here, and I either took this right out of the OpenStax textbook, or I created this myself by hand. I'm pretty sure I snagged this one from somewhere. But what we have here is the arc length model really is just dealing with infinitesimal little distances along a curve. And what we do is we integrate all those little infinitesimal distances together to get the overall length of the curve. All right, so a lot of hand waving going on, but if you think about area under a curve, so integral calculus, the very basic stuff, you find the area of a single rectangle, then you integrate with infinitesimal width, so teensy tiny in terms of the width, but then you integrate all possible infinitesimal width rectangles from A to B, put it all together, and now you have the sum total of the area under the curve, right? That's what's happening here, except we're doing it with little teensy tiny arc lengths along that curve, all right? So what we need to do is somehow kind of make this work for parametric models, all right? So internal debate. Yeah, okay, I am actually going to show you where it came from now. So, because it's pretty interesting. So here's the old school Calc 2 arc length formula. I'm calling it Calc 2 arc length for lack of better term. All right. And I'm going to refer to the diagrams here because they're there, so why not? So we have that little infinitesimal distance, right? So that little infinitesimal distance, you can see a little box here that gets pulled out, zoomed in upon. That's what this is supposed to be. It's supposed to be the zoomed in version of it. So we know that there's a Pythagorean relationship between a horizontal and a vertical distance. Right? We can get the hypotenuse just by using the Pythagorean theorem. So all we're doing to get that hypotenuse is taking the square root of x squared, well, normally x squared, plus y squared, but in this case, dx, that infinitesimal distance along x, and that infinitesimal distance along y, squaring them, adding them together, and then throwing a root on top of it, right? But the way we get the arc length is by integrating that over the interval of a to b, right? So s equals the integral over a to b of the square root of dx squared plus dy squared. Right? And so we need to integrate this with respect to some variable. And now you can kind of decide on your own which one you want it to be. If you're integrating with respect to y or x, it really doesn't matter because that infinitesimal change could be in either direction. All right? So let's say we're doing it with respect to x, so dx. All right? So what we're going to do here is just apply some algebraic skills to clean it up a little bit. But you could also go the other way now that I think about it. But let's just kind of go down this rabbit hole. So we have dx squared and dy squared dx. But we also know that there's a relationship between the derivative functions and the function themselves. So we can say we have dx dt. Sorry, water. Go too long without drinking water. I get what everybody else gets when they go too long without drinking water. That was extraordinary. All right, so what we can do is we can perform a substitution. All right, so we can say something like x equals t. All right, we can make that substitution right off the bat and go from there. All right. The other possibility is that we can actually work this out algebraically. Right. So we can actually handle it in that regard. All right. Hold on one second. I'm sorry. Let me just pause the recording. I gotta. Yeah. So. So as I was saying, you could go back to this idea of x being equal to some value of t, but this is something that we're not comfortable with from before because when we were putting something in parametric form, it became such an arbitrary thing where it was like, well, is x even really equal to t? So this is not something that we can assume, but it would be a way to get a relationship. Now, if you can get that relationship, then you're in pretty good shape. All right. So actually a lot better shape than what we're going to be in, but it's still not that bad. So what we're going to do, like I said, is we're going to do an algebraic approach where we're going to try to just kind of clean this up a little bit. So we have the integral from a to b. We have dx squared, dy squared, and then we have that floating dx on the outside. But what we could do is we could factor out the dx squared, which is kind of weird to think about because it's like factor it out from what? But if I divide each of these terms by dx squared, I'm going to get the 1, or I'm going to get a1. plus dy squared over dx squared.
How?
Because all we're doing is dividing each term by that dx squared. So I'm just going to clean it up a smidge. We still have that dx on the outside. So just kind of carry it out the other way. If I were to distribute through the dx squared, I would get dx squared times 1, which would give me dx squared. And then I'd have dx squared times dy squared over dx squared. The dx squares would cancel away. So it's a little nifty trick, and it's also something that might have a little familiarity because you did something like this with trig substitutions back in Calc 2. So there's something to that. You know, but the benefit of doing this is, well, it's two or threefold. One is that I can now take this out of the radical and make it a coefficient. I could also rewrite what's inside as dy dx squared. And then I have that, I still have that floating dx on the outside. I'll leave that black. And I'll leave this a to b. All right. Now, ultimately, we're looking to get to a rule. You know, so we have, and I'll bring it back in a second, but we have this dx dt squared plus dy dt squared dt. And this ain't that. But we also have, if we just kind of reflect back to what we did before, we have a relationship for the second derivative. I'm sorry, not the second derivative, the first derivative squared. Well, we have a relationship for the first derivative. We just need to square it. Dy dx is the same as dy dt over dx dt. All right, so so I have my dx. I have 1 plus dy dt over dx dt squared dx. So I could square each part. Or I can manipulate some things, but the better bet is to square it, get a common denominator, and then go from there. Or at least that is a way to go. But I still have, well, I got these two dx's here. So I'm just going to consolidate those. No reason why they still need to be apart. So if I want to get a common denominator, I need to multiply the top and bottom of the number 1. So that 1 is really thought of as 1 over 1. I'm going to multiply the top and bottom of that by dx dt squared. All right, so a couple of algebra steps here combined, but it should be okay. So we have a dx squared on the outside. So I'm going to have a dx squared, I'm sorry, dx dt squared over dx dt squared. That's to get my common denominator, plus dy dt squared over dx dt squared. Poor quality underlining there, so let me fix that.
Are we gonna have to know this process for a test or anything like that?
I was hoping nobody would ask that, at least until we were all in a better mood. Yeah. Sorry.
All right. It's
Yeah.
okay.
On every test, I always put one proof. And so this a proof or a derivation, and this is an example of one of them. What I'll do, and you could look at the review problem set before the next test. It's already posted, but you can see that I'll give you a selection of different possible proofs that I could ask. And unfortunately, this is one of them.
Okay, thank you.
So we have the a to b. We have that common dx dt on the outside. I'm sorry, on the denominator that can be pulled to the outside because it's a common value squared. But I will show the intermediate step here. Where we put the two fractions together. And we still have that dx squared on the outside. So, you know, I don't expect everybody to have memorized the arc length formula already, but if you refer back to it, you can see that it's kind of shaping up. You know, it's getting closer and closer. Right? So we're looking.
Can you scroll up just a little bit? I'm sorry.
Yeah, not a problem. Is that good?
A little bit more.
A little bit more.
Thank you.
No problem. So we have that floating dx squared on the outside, but we can now factor out, or at least just square root out the dx dt squared. We're going to take the square root of that, but that's a denominator. So we're going to be looking at integral over a to b, 1 over dx dt. Then we'll have our radical with all that good stuff in it. Can't draw. I think I just have to live with it. I'm going to just keep deleting and rewriting. All right, so we could do a little multiplying by the reciprocal, and then we'll be in pretty good shape.
Thank you, Professor. I got it.
You got it? Okay. Except I seem to have an extra dx here that I'm not thrilled about. So I just want to see where I pick that up. C equals all right, well, in the next step, keep, change, flip. Becomes dt over dx.
Was it right at the beginning where you factored out the dx?
I think maybe that's what I was just looking at. Let me scroll up to that in a sec. Because we're about to be right there, except I'm going to have an extra dx that we don't want. Where I factored out the d. Oh, all right. This is some tomfoolery action here. I threw the dx in at the end of the original formula because I misremembered the formula. Because in the Calc 2 formula, it's s equals the integral on a to b of the square root of 1 plus dy dx squared dx at the end. So it already had the dx accounted for. So this shouldn't have been there. That one's on me. I got all these extra dx's that never needed to be there. So I'll leave this up in its entirety, just so you can have another look. I'll also talk it through in a minute. But the next step here would be to kill the dx's. And then we would have we have what we were looking for to begin with. Yeah, so I'll send out formulas, and I'll put it on Blackboard too. I gotta remember to do this stuff because it's pretty important. The formula for arc length that got us started on this was the incorrect formula. So that's where the issue became. It spiraled out of control from there. I mean, the coughing fit didn't help, of course, and it's not getting any better. And I got to teach another 2-hour class after this, which will be fun. I don't know. Last class, I think I encouraged people to join that class because there was only 15 people enrolled in it. Well, now there's 30 people enrolled in it. So yeah, it's not a small class anymore. But anyway, so yeah, the correct original formula ought to have been I'll just chuck it in here. S equals 0 on the integral of a to b. I almost said 0. I don't know why. 1 plus dy dx squared dx. However, I don't like starting with that formula because it does like all the work for you, right? Because it kind of jumps you all the way down to this area over here, this part of the process, without you really getting into the nuts and bolts of the algebraic skills involved. So it kind of defeats the purpose, but that's where, people keep track of this sort of thing. That's where I had that extra floating dx in my brain that shouldn't have been there, right? So I don't know if maybe I'm talking more to the trolls on YouTube than I am to you all, because you all seem like very understanding people. So yeah, anyway, that's the formula and the genesis of the formula. Now, this is, like I said, it's a living document. You're remote learners, which means that you have access to all of this. If you go to the class notebook on my website, you will see, once I exit out of this app, you'll see that this is available to you. So you can just digest all of this. And if you need another look at it next class, I'm happy to go over it again, because again, the coughing fit, the mistake in the beginning, and also I kind of like the material, so I don't mind doing it. And by I'm trying to be cool about it. Like I really, really, really like it. So I'm absolutely happy to go over it again. But what I'd like you to do before then, or at least try to do, on the next page, we have there's several problems, but these are procedural type questions. All right. So numbers 1, 2, and 3. 1 is just straight up find the derivative and second derivative. So that one you should have a fighting chance with. All right, just you're taking derivative, you're following the process. Numbers 2 and 3, you might have a little bit of trouble with, but I'd like you to try it. Give it a whirl. But if you struggle with it, I don't want you to lose any sleep over it, because there's some skills here that you probably, or you may not have seen in a while, right? And there's also some kind of quirky bits related to parametrics that make things not necessarily work the way you would expect them to, right? So definitely see if you can get most of the way through number 1. Numbers 2 and 3, give it a good honest effort. Give it a shot so that you have a little bit of a frame of reference when we start going over it next class. But like I said, don't lose any sleep over it if you don't get it, because I haven't taught you how to do it yet. All right. So, but it's kind of like, let's see if you can do it before I teach it, because then the learning will have already happened. All right. So that's where we're going to leave it for tonight. I'm going to stop the recording.